Okay, and full screen OBS. Okay, so yeah, before we get started, right? First thing to do is to remind everyone that we have the our exam on this Wednesday, on 3 p.m. is during our lecture time, and the exam timing is from 3 to 5:30 p.m. So as I've already explained last time, but let me repeat again just to make sure everyone knows, because this is important, is that our exam is supposed to be 2 hours, and then the remaining 30 minutes is for you to scan and do whatever you need, right? So what we will so the way we will do our exam is that we will be you can find it in later. The exam will be unlocked during the exam time. You can go and see the question and also download the answer book. Okay, so the way we are doing exam in our university is we will have the answer book, and then this for you to write your student ID and all your details information. And this one is like just like any other exam, or they have instructions to candidate and things like that. And for the online case, what you can do is you can add pages. You can answer whether it's by handwriting or however you prefer, and then you include this as the front page. Okay, so so you can, yeah, so that one, it depends on what software you use. You can paste together in one page, or do whatever that you whatever that is necessary, right? But so these are like just some side details, and I suppose the more important thing is yeah, everyone study for the exam, right? Make sure you know how to solve the question. We will be covering chapters 1 to 5, and yeah, so we will have 5 questions, and each 5 questions have different parts, so you can try to solve them, and yeah, try your best to solve them. And then other than that, that's pretty much it, right? Just solving physics question, right? All the things that we have been learning so far. All right, so yeah, I think, yeah, that's the important things I want to say. So does anyone have any question about the exam? Let me see. Each chapter 1 question approximately, yes. Yeah, how many questions are? Yeah, I think 5 questions, so each chapter 1 question. The Moodle says 2:50 a.m. Don't worry about this at the moment. You mean right now on my computer, is it? Yeah, because yeah, it's a bug. The clock on my Windows is wrong. So but if you open it, it should be showing the correct time. But anyway, during 3 o'clock everyone will be here, right? So if there's any problem, we will fix it. So don't worry about the 2:50 a.m. part. It's the Windows clock. It also says 2:50 a.m. is it? Oh, okay. I go and look at it later. Yeah. Yeah. So this kind of thing happen every time I switch between Windows and Linux. Need to join Teams in the midterm. So not compulsory, but I will start a meeting so that if anyone got any issue, right, you can communicate with me for on the Teams, right? Not need lah, but I think in case, you know, so that I'm around, then I'll be on the Teams. Yeah. Yeah, I'm gonna look at it later. So maybe it's because I do the setting when I'm in the Windows mode, so that's why the clock is wrong. I go and do that in Linux again later. The clock in my Linux is the correct one. Okay. Any other question? Yeah. So today there's nothing much I want to rush to cover, because we just need to finish one last topic about rolling motion, and after that, after we finish rolling motion, is going to be the new chapter already. So that when we come to the new chapter, yeah, so it's not a how to do the question. You can find me lah, but then I will be quiet and cannot answer you. The midterm cover chapter 6. Yeah, I will start the Teams meeting. Yeah, I will start the Teams meeting just so that I'm available. midterm does not cover chapter 6. Okay, so if we'll do things like in chapter, yeah, so as you can see, right, I show you what we did in chapter 5. Chapter 5 and 6, where is it? Yeah, so we have 1 2 3 4 5, right? So we only do it until here. So these are the things that we did in chapter 5. Remember, right? We were discussing all this angular motion, the rotational kinetic energy, the parallel axis theorem, and also like how to solve this, using the conservation of energy, from converting kinetic energy into work done, this kind of thing, right? And then after that, chapter 6 is what we are doing now. Okay, talk, no, because talk is in chapter 6. See, talk is in chapter 6, remember? Yeah. So okay, yeah, so unread messages, where? Okay, yeah, so that is about it lah. I think that's the important thing, right? And so usually, yeah, I know students will be very stressed when it comes to exam and things like that, but yeah, try not to be too stressed and try not to be too panicked, right? It's just the exam, and you will have many more exams in your many semesters here. So yeah, if you think too much about it, then the more stress you get, right? In any case, let us start talking about rolling motion. And I think today is going to be a bit of a relaxed lecture as well, because after finishing rolling motion, I don't want to start a new chapter, because you already have so many things to be studying, right? Chapters 1 to 5. So I will start chapter 7 on next Monday after our exam. But let us finish off rolling motion, right? So I'm in Windows now again, because yeah, so I want to show you the animation in more detail. Last time in the previous class, we were running out of time, right? So I didn't have enough time to spend to show you all the details about the rolling motion. So let's talk about rolling motion now properly. And yeah, so we're gonna spend basically 2 hours on it. So what is rolling motion about? Okay, so rolling motion is about the motion of an object rolling along usually it's on some surface, but generally speaking, it could be anywhere, right? So we have some sort of a rigid body. Rigid body has some size, and is there a message? No. So the rigid body has some size, so it can rotate. And if it is not attached to any pivot, then naturally the rotation will be around the center of mass. So there's going to be 2 types of motion that you want to keep track of when we are talking about rolling motion. So translational motion of the center of mass and the rotation around the center of mass. Okay, so yeah, so usually what you see is an object, right, rolling along some surface. Okay, the center of mass is going in some direction, and at the same time it is also rotating with some angular velocity. So the way to solve a rolling motion is, usually students find it very confusing, because right now we are mixing 2 types of motion at the same time, so it's very hard to imagine how the situation works. But actually, if you just follow everything that we have been learning so far, it's very systematic, doing it step by step. What I mean is systematic, right? Center of mass, we solve it using Newton's laws, right? So Newton's laws, right? In particular, we were talking about F equals to ma, right? And this A, using Newton's law, you can draw the free body diagram and everything, and to determine the net force acting on the object. Once you determine the net force, you should be able to calculate the acceleration, and this acceleration is the acceleration of the center of mass, right? So once we have calculated the acceleration of the center of mass, using the acceleration of the center of mass, we can calculate the velocity, the position, and whatever things you need, right? So that is what we have been learning from chapters 1 to 4. So that one is pretty straightforward, right? We have spent a lot of time doing on it already, right? Either momentum, angular momentum, kinetic energy, things like that. right? We use the linear Newton's law. For the case of rotation, we determine using the torque equation, right? So the torque equation is the torque is equal to I alpha. This is the net torque acting on the object, right? There could be more than one torque that will apply to this object. And once you have solved this equation, we have also been spending chapter 5 learning how to calculate the moment of inertia, chapter 6 figuring out the torque, and once we have the torque, we get the angular acceleration. Okay, so angular acceleration of the rotation of the object, right? So once we got the, after we got the angular acceleration, we can get the angular velocity, angular position, and so on and so forth, right? In particular, we can also calculate the v tangential. So from here, we can determine the v tangential of the object is equal to the radius of the object times the omega, right? So a rolling object will have two types of velocity, right? So we got v center of mass and then the v tangential, right? So using these two, we are able to determine these two quantities. Okay, so let me draw this. Yeah, so I should draw it a bit more clear. This is the important part here. This is where yeah, I want to go a bit slow to explain because we have plenty of time and it is potentially confusing. So when the object is rolling, right? So let's say it's rolling like this. Okay, so let's say it's rolling and then the center of mass is at the middle. Okay, usually this is the case. Usually we consider uniform objects or uniformly distributed, spherically distributed objects, right? So what we have here is that if the object is rolling, we have two velocities. So velocity is a vector, right? Velocity is a vector. The magnitude is the speed. So this is the center of mass velocity. And if you follow one point, right? So let's say this is point P. Then at that point P instantaneously is having a tangential velocity, right? So it's having a tangential velocity because of the rotation, but at the same time, the whole thing is moving with the VCM as well. So we can use this concept to calculate the net velocity or the resultant velocity of point P is given by v, let's say the velocity of point P is just the v center of mass plus the v tangential. Okay, so that is the important equation that we need to remember in order to visualize the rolling motion. Okay, because things will become more and more complicated later, especially when we go to talk about rolling with slipping. So that will be a bit more messy if we forget this equation, right? So what is the net velocity? So let's look at it. This is two vectors, right? So I have a VCM, right? And then I have a V tangential. So I can add up the two vectors, something like that. And then the velocity when it is here, the net velocity is given by this equation here. So this is velocity at point P, right? So the way I draw it is point P happens to be at this position. But as the thing is rolling, right, the P will move to somewhere else. When it moves to some different places, the VCM remains the same, but the V tangential, well, the direction of VCM remains the same, right? Magnitude, don't know, maybe got acceleration. You know what I mean. VCM direction remains the same, the V tangential direction, right? When it comes to here, like at a different place, it will become some different location, right? So when it comes to a new point, let's say P prime, right? So then the equation now becomes VCM, right? And then the VP becomes like this. So the net velocity will become a different vector, right? So the total velocity of a certain point P will be changing throughout the motion. Okay, so it covers all the special cases. For example, if the thing is not rolling, right, if it's just sliding over the surface, then V tangential is 0. So VP is just moving horizontally following the center of mass. That is one special case. Another case is VCM 0 is just spinning in position, what we have been doing in chapters 5 and 6, right? VCM is 0, is just spinning in position, so the V tangential is going in a circular motion. It's always tangent to the circle. Okay, so that it covers the special case. Maybe I should write it out. Okay, so special cases. right? So very quickly, the VCM equals to 0. Then this gives us the rotation, right? Rotation, pure rotation. Okay, so pure rotation. Then P going in circular motion, right? And then the other special cases is V tangential is equals to 0. This is just pure translation. And then P is in linear motion, right? So at every stage of the motion, right, the translational motion is given by your linear Newton's law. The rotational speed V tangential is given by calculating the torque. Okay, so we have learned how to solve this separately already. So it should be easy to combine them both at once, right? It should be easy. Okay, so it's only complicated because we bring over our imagination, our everyday, preconception into this. But other than that, it should be pretty straightforward. Okay, so yeah, so that is the idea of the rolling motion. And as we have started talking about in the previous class, is that there's two types of rolling motion that we want to consider. Let me start a new page. The type of motion, we will consider two types of motion. Two types of rolling depends on the speeds, right? So the speed, I want to talk about the VCM, which is the speed of VCM, the magnitude of this vector, and the speed of the V tangential, which is the magnitude of the V tangential vector. And V tangential is given by R omega, as we have been learning how to calculate, right? So yes, usually every time, right, every semester I teach this type of topic, student always mix up these two things, and that is where all the mistakes come in. As long as you remember to keep track, right? When we talk about center of mass, means center of mass, right? And V tangential is R omega. So these are two separate things we should. Then the way to solve it is actually very simple. Okay, so when you actually see the calculation and the solution, the equation actually is like very short lines only, and then we just need to know how to match them nicely. Okay, so there's two types of the motion that we want to study. So this is pure rolling, or sometimes we say rolling without slipping. So this thing happens when VCM, the magnitude, is equals to the V tangential, right? The magnitude, right? So after you take the absolute value, both are positive numbers. We see what are the numbers, okay? And the other case is rolling with slipping, okay? Is that they are not the same. Okay, so what are the implications when they are not the same? So I will show you next. Okay, so what happens to VP if V tangential is the bottom? Yeah, so this is what I want to show, right? So let's so I will draw it, right? And if it's not clear, I will go to the animation, then it will be more clear. So let's draw a rolling object again. So something round, right? Usually if we are solving for something round, like a wheel or a ball, right? Depending on the moment of inertia. Okay, so the VCM is always like this, right? So VCM is like this. So let us consider so let's consider a pure rolling case. So pure rolling case means VCM is equals to V tangential, right? So VCM equals to V tangential. So the speed is the length of this vector, right? Okay, so let's look at P again. So let's try to draw something with the same length. This is V tangential vector, right? So then as I've been saying, the point P is the vector sum of these two vectors. So V tangential plus VCM. So just the same thing I draw last time. But you want to know what happens at the bottom, right? Sleeping. Yeah. I know, right? Monday is still morning, so everyone Still feeling sleepy, including myself. Rolling with sleeping. Rolling with slipping, right? So rolling with slipping is slipping. Yeah, the word slipping means is sliding over, where there's sliding over the surface, right? So that's where the word slipping comes from. Before I get to the bottom, right, let's see what happens at the top first. Okay, so when my point P is at the top, right, what is my V total, right? So my total vector is the sum of these two vectors. So I have a VCM pointing forward, and then another V tangential also pointing forward. So my net total velocity VP, right? In fact, the magnitude is twice of the pure rolling case is equals to some V, so it's twice, right? So when the thing is at the top, the velocity, if the whole thing is moving at speed V in pure rolling, the point P at the top is instantaneously 2V, right? So it's easy to imagine, hopefully, because it's the vector sum of these two velocities. Now, what happens when P is at the bottom? So when the time it rolls to the bottom, right? Okay, when it rolls to the bottom, then the tangential speed is going here. Okay, and then but at the same time, the VCM is in the opposite direction. So when this happens, so these two vectors are opposite. Two opposite vectors, same magnitude. So this vector plus this vector, you get 0. Okay, so the instant it touches the floor, at that one instant, is having a 0 velocity. But immediately after that, it will have non-zero velocity again, because it will roll, the direction changes. Okay, so that is what happens in the pure rolling case. So pure rolling case, when everything is moving at the speed V, the point at the top is 2V, and then go to the bottom is 0, right? And then 2V again, and then 0. And intermediate, the magnitude will be changing. Okay, so is that clear? Okay, yeah. So so let me show you the animation again. Right? Oh yeah, I'm supposed to upload this, right? So let me upload this after this class. So we're talking about a rolling motion, right? So this is a real time to show you where are all the vectors. Okay, so the standard picture, my point P is over here. Wait, I should carry this out of the OBS first. Okay. So as you can see, at that instant, right? My point P is over here. The blue vector is horizontal, is the VC, and this is V tangential. So the vector sum is this vector plus this vector, so you got this direction, right? So this is pure rolling case. That means the magnitude, the length of these two vectors are the same. Okay, so you see what happens when it goes to the top. Okay, top. Not fast enough. Right, so roughly around there near the top, right? So the two vectors add up, you have twice the length, the resultant speed, right, of the VCM. So this is 2V, right? So when it comes to this direction, then the net vector is here, right? But when it goes to the bottom, at that instant when it's at the bottom, the two vectors, they cancel each other out. So the two vectors cancel each other out. So at that instant it has 0 velocity. Right, so this is pure rolling. Then throughout the entire motion, you can see how the vector changes in the entire time. Okay, so that is the case of pure rolling. Okay, so does anyone have any question? How to calculate friction with rolling? Yeah, I will show you that later. So yeah, we will have an example later at the end of the chapter. It's a constant with respect to velocity at the point. Yeah, I mean it's the same thing, right? Yeah. So I will show you how to calculate later. That is rolling with slipping, right? So we do the pure rolling first. That is kind of the easier case. If it's pure rolling, it must be 0. Yes, what you mean? It must be 0 at the bottom, right? So at the bottom must be 0, but at other place you see it's not 0, right? You can see the vector here. Okay, yeah. So we're gonna come to that later after we figure out pure rolling. Okay, so for pure rolling, it's like this. Okay, so let us yeah, to actually, so these are like animation and stuff, of course. To actually see how things work, we should try to work out an example. So let me pull up the lecture notes. Okay, 6.5.1. Okay, so you got this picture here as well. You can take a look at it. So a typical rolling case, right, is this. A spherical boulder of mass m, radius r, rolls without slipping down a ramp at angle beta, and use this information to calculate the acceleration. So where's my full screen? Full screen. Okay, so let's figure this out. Okay, so we are doing 6.5.1. Okay, so I have a boulder rolling down a hill. Okay, so looks something like this. Okay, so if you watch the movie Indiana Jones, right, at the beginning of the movie, there is a boulder rolling down a slope, and the boulder is chasing after Indiana Jones. Okay, so we got this situation here, right? So the radius of the boulder is r, right? And so this is a boulder. Did the question say? So the question say it's a spherical boulder, and since it did not say the mass distribution, it is fair to assume it is a uniform sphere. So it's 2/5 mr square, right? So this is the moment of inertia. Remember, we spent a lot of time deriving this equation, right? So hopefully everyone can remember 2/5. So how do we calculate the linear acceleration? So how do we solve this system? So always remember, right, this is a rolling boulder. So it's a rolling boulder, so I have two types of motion. So two types of motion, we're going to do it piece by piece. So firstly, let's start with the translational motion. So let's look at the free body diagram to solve the translational motion. So for translational motion, right, we use the free body diagram. Okay, so what are the forces acting on the boulder? So just solve it like a normal center of mass situation, right? So do our normal usual method. So firstly, the free body diagram, what are the forces? The forces is there is a weight mg, it is touching a sloped surface, so there is the normal force as always, right? And then so when it comes to rolling, right, so there's going to be a friction. So so there's a friction, so let me say the friction is acting in this direction, and it is a static friction. Okay, so now are you guys happy with this? So this is the point where things start to get weird with for first time studying this, students studying this for the first time, right? So I draw the static friction in this direction. Okay, but remember, right, static friction is automatic response. It is going from 0 to the maximum depending on how the situation around him, the static friction. Do you remember, right? So when it comes to static friction, right, especially when solving rolling motion, we know it's along the surface, definitely, right? It's either you can choose whether to do it here or do it here. Okay, so we can do it in this way. But you can, so how do you decide which direction to put? So here is the nice thing about Newton's law. Actually, as long as you get the parallel direction, it's fine. If you guess the wrong direction, right, then don't worry, the answer will just be a negative sign. We'll give you an extra negative sign. As long as you do everything correctly, you get an extra negative sign. Once you get a negative sign of the friction, it means that you should have drawn it the other direction at first, right? And then once you draw the correct direction, you solve it again, you get everything correct. You know what I'm saying, right? So hopefully, yeah, hopefully that makes sense. So right now, let us try to resolve this situation. So the axis I want to draw is my positive x is in this direction, my positive y is in this direction. So if I resolve this, then let's resolve the weight. So the weight I got mg sine beta, and then over here I got mg cos beta, right? And then this is parallel to y, this is parallel to x already. Okay, so the y for in the y direction, I got n minus mg cos beta is equals to 0. Therefore, n is equals to mg cos beta. So I got the equation for my normal force, right? And what else? The other thing is the x direction forces. So my x direction forces is I taking forward to be here. So mg sine beta minus fs is equals to mass times the acceleration. So this acceleration is the acceleration of the center of mass, right? Nothing to do with tangential motion yet. Okay, so this is my second. So this is my second equation. Okay, so does everyone follow the story so far? Okay, so hopefully it's fine, right? Because this one we are just treating it like a normal chapter 2 question. A block sliding down a surface, there's friction, so so they got this. The only difference is this is static friction. Why? Because pure rolling there is no relative motion. It just touches the ground and continues to roll. So this is static friction. Okay, so this is what we have so far. Then the next thing to solve is the rotational motion. So we look at the torque acting on the system. So what's the torque acting on the system? Okay, so we already identified the forces. But the mg passes through the center. So the distance from the axis of rotation is 0. The normal force also passes through the center. So it gives 0 torque. So these two things does not cause the object to rotate, right? But the friction that we have drawn here will contribute the torque. So my friction is along this direction, and it is at a distance r away from the axis of rotation, and is perpendicular, right? So how do we get the torque? So starting with the general formula, torque is equal to I alpha, but in this case the torque is the distance times the static friction, and then I alpha. So I is the moment of inertia, so it's 2 over 5 mr squared, and alpha is the angular acceleration of the rotational motion. Okay, so it's not related to the linear motion, not yet. Okay, so it's not yet, but if it's pure rolling, we can combine the two. Okay, so right now what we have here is this. Okay, so we simplify this equation first. So we have friction is equal to 2 over 5 mr alpha. Okay, so so we have this third equation now, right? So I got these three things now. Okay, is anyone confused yet? Before I continue, right, I want to make sure no one is confused before I continue on. So everyone is okay, I hope. Okay, yeah, because the must be careful at this stage, right? When you know, if someone is confused, then the more I explain, the whatever I explain afterwards is no point, because we already cannot follow the story, right? V tangential always equals to VCM in pure rolling. Can there be cases? Yes. So that in this case it will be non-pure rolling. So which is the case we haven't studied yet, right? So right now we only study this these two cases. So so this Windows always like this. So yeah, so it's either VCM greater than V tangential or VCM less than V tangential. So you are talking about case 2. So we will do it after this. Okay, so there's two cases to consider here. So right now we are still assuming this. Okay. Yeah. Okay. Click. Okay. So I think so. Everyone should be okay now, right? Now, how to solve this question, right? So I have well, I have a bunch of equations here, but this is the part where we can carefully connect the two equations together. So right now, right now what we have here is yeah, no space. So okay, so right now, right, what we have here is this. This situation is pure rolling. So pure rolling means the VCM is equals to V tangential, right? VCM is equals to V tangential. So so VCM is equals to V tangential. That means, and V tangential is R omega. So R omega. So that means VCM is equals to R omega. Okay. So pure rolling is about the velocity. But what the equations I have here are acceleration. Never mind, because we just need to differentiate both sides of the equation. Okay, the radius of the thing is constant, right? It's always the same sphere. So we differentiate both sides of the equation. Right? So this becomes the acceleration, which appear in this Newton's free body diagram. And on the right hand side, differentiating omega gives you angular acceleration. Okay, so from here we conclude that the angular acceleration is just the linear acceleration divided by r. This is for pure rolling. Okay, so only for pure rolling we can do this. And since we can do this, we can substitute this into here. Okay, so we substitute this into here. So what we have, so the friction on this thing is 2 over 5 mr, and then alpha is a over r. So I can cancel this r. So the friction is 2 over 5 ma. So I got the third equation now. Okay, so right, so now we got a simple equation for little f, the friction, and then I have another equation over here, which is little f here. So what I can do is I can solve this simultaneous equation, right? So I'm going to take equation 2 plus equation 3. Okay, so this equation plus this equation, I will cancel the left hand, the fs on both sides. Then I just left with mg sine beta, and then this plus this, so ma plus 2 over 5 ma. So this plus this is 7 over 5 ma, and then this is mg sine beta. Okay, and both sides cancelling the m, I can calculate my acceleration now. So my acceleration is 5 over 7 g sine beta. Okay, so this is, see, the acceleration for rolling is different from just a box sliding on over a surface. Okay, so we have found the acceleration in this way now. Okay, so this is my so this I didn't say, but this is supposed to be the center of mass acceleration. Okay, so any questions so far? Okay, so hopefully everyone is processing this nicely. So normally for a linear box with no rotational motion, right, do you remember what was the acceleration? You just resolve and then you get g sine beta and then minus whatever is the friction, right? But this one is very specific, right, for a pure object just purely rolling over a surface. But now that we got the A already, we can calculate the friction. So calculating friction. Friction. Right, so Fs is equal to 2 over 5 ma, and we just put it inside here. So it's equal to 2 over 5 m, and then 5 over 7 g sine beta, right? Pretty straightforward. 5 cancel with 5. So the static friction acting on this system is 2 over 7 mg sine beta. Okay. So the mass won't affect the acceleration of the wheel. Yeah. Yeah, so seems like our answer is independent of mass, right? Correct. What it will, so, okay. So, let me add on some extra things. So we have solved the two things that the example is asking for, but we can actually do more things related to this. Okay. mg and cannot because the torque is equals to 0. Correct. Yes, 志浩. So because the mg and n pass through the axis of rotation. So the axis of rotation is here. So the distance from axis is 0. So 0 torque coming from these two. So there's only one torque coming from here. Okay. Yeah. Any other question? What time is it now? Okay, pacing is good. Okay, so what was the extra thing I wanted to say? So when we solve this, right, there's an assumption over here. This is static friction. Remember, static friction has a maximum magnitude. If you exceed the maximum magnitude, it will become kinetic friction, right? So this we have assumed we are Fs is maintained. In other words, Fs is between 0 to mu s times the normal force. Okay, so now let me do something extra. We can actually determine the situation where when does the static friction is lost, right? So that means when does can I exceed this value? So when I exceed this value, what happens, right? So let me see, right? So let us calculate, right? So we need the mu sn. So for so what happens here is that remember, right, static friction exists in a range. So it looks like our expression depends on beta. So when the beta is 0, there's no static friction, right? So nothing happening there. When beta increase, static friction will automatically increase to satisfy this equation until it reaches the maximum. So when beta reaches a maximum angle, then my static friction becomes the coefficient of static friction times the normal force. So my equation now becomes mu s times n, and then 2/7 mg sine beta max. Okay, so I can increase until the maximum angle, and when I increase the angle too much, it becomes this situation. So what happens here? So there's an n here, right? But I have a formula for n just now. So a formula for n, which is mg cos beta. So let's see what happens. Right, and then this is 2/7 mg sine beta. So I want to find the beta max. So these two angles should be the same, and we seem to cancel the mg on both sides, right? And then if I bring this down, I get tangent beta maximum is equals to 7/2 mu coefficient. Okay, so my maximum angle is what? The inverse tangent of this thing. Okay, so if I increase more than that, so if I increase more than that, what happens? So if beta is greater than beta max, then no more static friction, right? So no more static friction. And in all the example that we solve, right, when we say when there's no more static friction, becomes what? It becomes the kinetic friction. Okay, so when it becomes kinetic friction, this is what we'll talk about next. Is it becomes rolling with slipping. Okay, this is important to remember. What do we mean when there's kinetic friction? So kinetic friction means relative motion between the surface, right? And static friction means no relative motion. Okay, so and where does the no relative motion come in? So we will bring back in a full circle, right? When we talk about pure rolling, the two surfaces is the surface of the object, rolling object, and the ground. Okay, So the instant it contact with each other, the v is 0. So there's no relative motion. So it's at instantaneously it's just touching, right? That is where it's pure rolling, and this is why when we talk about pure rolling, the friction involved is static friction. Okay. So yeah, so do you understand so far? Do you follow? So I know, right? This chapter is the one of the challenging part, and is based on how we the last two lines again. You mean this one? Yeah. Okay. So this is the interconnected. This is the connection between rolling, pure rolling, and static friction. So when we are still talking about pure rolling. Actually, I saw a bit ahead already. But when it comes to pure rolling, right? When it comes to pure rolling, there is no relative motion between the surfaces. Okay, there's no relative motion between the surfaces. So if the surface has friction, it must be static friction. The static to not static. What? Oh yeah, so that's what I say. So okay, right? I think at this stage, for static case, pure rolling, everyone agree, right? Okay. So in this part, what I calculate is, because static friction can break, if I exceeded this range, static friction will become kinetic. So let me try to see what happens. If I increase the beta, right? If I increase the beta too much, it will become kinetic friction. Okay. So let me find something round to show you. Okay. So let's say I have something rolling, something to roll on. Wait. Props. Okay, so I have a angle surface, right? And I have this. Okay. So if my angle is roughly small, right, it will just roll nicely over the surface. Okay. So that is what we are calculating over here. And then the acceleration and the friction is based on the angle. So everything here is pure rolling, right? So it's very hard to see, obviously, but it's pure rolling, like you can imagine, right? But if I increase the angle too much, right? If I increase the angle too much, what happens is, if I increase to beyond beta maximum, then it becomes kinetic friction. So that means it's no longer rolling around. It's just sliding over the surface, right? It will rotate a bit, right? It will rotate a bit, but the VCM will no longer be the same as V tangential, so it will be sliding over the surface, right? So it just slide over the surface, and the no longer a pure rolling motion. Okay, so hopefully you can visualize this using toilet paper. Okay. Any question? So how it become kinetic friction? Yeah, it just becomes kinetic friction when the V tangential is lower. Yes, exactly. So when you reach the maximum, static friction is not enough to provide the torque for the rolling object. Exactly. Yeah, that's a better way to put it. This is what I've been trying to say, but you phrase it in a much better way. Yeah. So the static friction is not enough to provide the torque. So then what happens is V tangential is lower than VCM. I think it's higher. Yeah. Actually, yeah. As long as they are not the same lah. So right now it's not the same. It could be higher. It could be lower. Slipping, correct. Yeah. So that's what I want to yeah. So slipping. So it is. It's not pure rolling. It's just slipping. Right. No longer rolling. Just slipping. Okay. Is that clear? Okay. So yeah, it is confusing, but the fundamental concept is there. So it's everything that we have been talking about. right? So for different questions also is more or less the same basic idea. So always remember to stick to the central concept that what we have been trying to do, and I'm trying to convince you to solve, is that we can solve them separately and we analyze what happens individually. When it's pure rolling, then the V tangential is same as VCM. If it's not, they are not the same. Correct. Yes. So V tangential is the velocity vector. Yes. Yeah. So yeah, still using this picture, right? VCM is the whole thing moving horizontally, but at the same time, V tangential is the tangential velocity at the edge of the sphere. For this problem, is the sphere. Okay. Yeah. Good. Good. Yes. Always good to make sure. Okay. So yeah, so let us go to the next example, right? So the next example is another pure rolling situation. You can actually solve, depending on what the question is asking, this type of situation, right? You can either solve it using conservation of energy, but right now we are learning about rolling, so we can actually solve it using torque and free body diagrams. So what we have here is like a yo-yo. Yeah, do you remember yo-yo? So yo-yo was super popular in the 1980s, and yeah, and it's made for this question, we just imagining like wrapping a massless string around a solid cylinder. So it's a cylinder, so the moment of inertia is half mr squared, since it's a cylinder. With radius mass m, radius r, the free end of the string is held fixed to the cylinder released from rest, like in the picture. So the string unwinds without slipping. Okay, and then find the speed and the center of mass after it has descended the distance h. Okay, so the picture looks like this, right? I have a yo-yo, right? And then yo-yo has there's a string roll inside, right? So if you let go, the yo-yo will unwind. Okay, so it will unwind and it will yeah, it will continue to unwind down. So we have the motion is from initially start from rest to here, the distance covered is h, and then it is, by the time it comes here, is rotating at omega, and the linear motion will be going at VCM. Right, so this is what we can do here. So actually we should use conservation of energy, so that will be easier to solve, right? So we can use conservation of energy because there's no external forces. It's unwind without slipping, so no kinetic friction, so no heat loss to the environment. We have conservation of energy. Okay, so what is the energy here, right? So so by the conservation of energy, right, I hope everyone is very familiar, is basically the potential energy at rest here is converted into kinetic energy here, right? So the potential energy is initially all in mgh, and this amount of potential energy will be converted into kinetic energy. So it will be translational kinetic energy plus rotational kinetic energy. Okay, so now let's put in the equations accurately. So the translational kinetic energy is the normal half mv squared, right? So half mv squared, the v here means the center of mass v, and then there's a rotation. So the rotation we have learned, right? Chapter 5 covered in the exam, half I omega squared. Okay, and we just need to know what is the I. Actually this is a cylinder, so I is half mr squared, right? So yeah, so might as well just put this in. So I is equal to half mr squared. So I'm going to put it into here, and this is unwinding without slipping. So unwind, rolling without slipping. The question say the string unwinds without slipping or stretching. So this is rolling without slipping. Rolling without slipping means the VCM the center of mass phi is equals to V tangential. V tangential magnitude is R omega. So V is equals to R omega here. So we can put this into here as well. Okay, so we got mgh is equals to half mvcm square, and then we put all the stuff in, so I got half mr square, and then omega square is just vcm over r, so it's vcm square over r square. Okay, then once we put everything correctly, a lot of things cancel, so these two cancel, the mass cancel over here, so I got gh is equals to half vcm square plus half times half, so it's a quarter vcm square. Okay, so if I make it the denominators the same, I got 3 over 4 vcm square gh. Okay, so I want to find vcm, right? So vcm is just 4 over 3 gh, and then you square root. Okay, so this is the velocity at the base when it descended the distance h. Okay, so find the downward acceleration of the cylinder and the tension of the string. So this one is where we need to use torque now. So let's see how to do it. Right, so this was part A. Right, now we want to solve part B. So again, we are looking for linear acceleration and the torque. So there's two types of motion to consider, the translation motion and rotational motion. So for the translational motion, we look at the free body diagram, right? So just look at all the forces acting on the cylinder. So as always, there is a weight, mg, and then it is hanging from a string, so there's a tension, right? And if I take the downwards as positive, I can write the net force. The net force is mg minus t. In the vertical direction is mass times acceleration. So this is the equation coming from Newton's law. And then we look at the torque. So torque is about the rotational motion. We look at the torque, right? So there's only one torque acting on the system, right? So the mg passing through the center. So yeah, so let me write extra steps to make it more clear. The net torque is what? So the net torque is tau net is equals to so we, yeah, I should say the direction, right? So let's say clockwise is positive, right? So it's increasing in this direction. So the net torque is this force times the perpendicular distance r. I draw it too small, but I think you know what I'm talking about, right? So this times this, and then mg times the distance. So mg has 0 distance from the axis. It's passing through the axis. So 0 times mg. So this term becomes 0, right? So the net torque is r times t, right? So the net torque will give you is tau is equals to I alpha, and this is equals to RT. So RT is equals to moment of inertia, which is half mr square and then alpha, right? So and then this is with rolling without slipping, so that my VCM is equals to R omega. So if I differentiate both sides, it's the same as differentiating this both sides. So I got linear acceleration is equals to R alpha. Right, so alpha is ACM over R. So I'm going to put this in as well. Okay, so what I have now is RT is half mr square. Alpha is ACM over R. So I can cancel the R everywhere. And I got this. So my tension is half MACM. Right, so I got 2 equations now. Right, so equation 1 and equation 2. Okay, so now we can solve the 2 unknowns. The question is asking for tension T and the linear acceleration. So the, well, it's very nice to cancel the T. So I just take equation 1 plus equation 2. Right, so this plus this on the left hand side just give me mg. This plus this is this plus half, so it's 3 over 2. Okay, so this is 3 over 2 MA center of mass. Actually, both sides cancel the M, so my ACM is 2 over 3 G. And then we put this in our tension, so my tension is half M ACM, which is 2 over 3. So cancelling, so I found my T as well is 1/3 mg. Okay, so we will realize that everything will be consistent with all the laws that we have been learning so far. Number one thing we notice is that, of course, if we let the yo-yo just unroll from a string, right, the acceleration is not equals to g. It's actually less, right? So it's not equals to g. And then secondly, the tension is 1/3 mg. So tension is not equals to the weight. That is expected because the net force is non-zero. That's why you got the acceleration. Just that the acceleration is not equals to g. Okay, make sense? Any question? Wow, this is 11. It's 11 already. So, yeah, sorry, I talked too long. So let us take a break, right? And if you have any questions, just type in the chat or you ask me. We have, yeah. So the next thing to talk about is just rolling with slipping. So let us take a 10-minute break. We will come back after this. Okay. Yeah. So I mentioned Indiana Jones last time because when I was teaching this in Singapore, I used this picture, right, to demonstrate a rolling object. But now, right, let us start to consider rolling with slipping. So let me remind you one more time, just to make sure we have an exam on this Wednesday. Okay, so yeah. And so you guys have done the thermodynamics exam already, right? So you sort of have an idea of how to scan your solution and things like that. So hopefully, yeah, hopefully everyone is okay. The classic booby trap, yeah, yeah, it's the classic scene from the movie. Any movie since then, like about exploring some archaeological site, will have all this type of situation, right? Like Tomb Raider and things like that. So am I recording? Test. I'm recording here. Yeah, doesn't have to be because now it's online, right, and everyone is stuck at home. Just use blank paper. Can we use tab? What do you mean? Oh, tablet tablet to answer. Yeah, can. Anything is fine. Yeah, Dr. Jones is the movie Indiana Jones. So scan from blank paper is also fine. And obviously you can't, right? So anything that you save, as long as at the end you have a PDF file, and yeah, so thanks Gloria to remind everyone, use the cover page. Okay, so if you use tablet, maybe it's more convenient. You can open the file using tablet and then you add new page towards the end. Otherwise, if you scan it, you just join the files together, or maybe you want to print this out and then you handwrite your answer and then you take picture. If you've done the thermodynamics exam already, you do it the same way, right? It doesn't matter. Okay, so as long as have something, as long as got some solution that we can see, then it's good enough already. Okay, so yeah, so let's continue. Now we are talking about rolling with slipping. Okay, so now when we talk about rolling with slipping, right, we will involve friction. So let us recall a few facts about kinetic friction first. Let us remind ourselves a few things about kinetic friction. So when we were solving friction, right, at the time in chapters 2 and 3 and so on, we are talking about just the object with the center of mass, right? And then if the object is moving at some velocity v, okay, the friction is always opposing the motion, right? So is when we draw the friction is like this, so Fk, right? So the important thing here is that Fk is opposing to v, so Fk direction, okay, and the magnitude is, we can do it in this way, right? So it's the coefficient and then times n. So depend on how you get the n, we can get the n by solving the free body diagram. So this type of situation, okay. So the thing that we want to remember is the kinetic friction is opposite to the velocity at the same time. So if the box is moving this way, the friction is going here. If the box is moving the other way, the friction is going here. So the friction, that's why friction is not, it's a non-conservative force. It doesn't depend on position, it depends on the direction of motion, okay. 10 minutes gone. 10 minutes, yeah, because talking about yo-yo, is it? If the question is taken from mastering physics, we can find, yeah, the question is not from mastering physics. Yeah, so but then mastering physics is, it has a lot of questions lah. So, and a lot of the mastering physics question is like very standard calculation question, and a lot of it is different, not to say all lah, but majority of mastering physics question is different style from what we have been doing here, right? So that is also another thing. And I have used mastering physics in the past, I don't like it, so that's why I avoid mastering physics. So you can't find it in mastering physics. Okay, you still don't know how to do after Google. It is kind of true also. Mastering physics, right? And because the Pearson textbook lah is under Pearson, is very, yeah. The question that they do is they use a lot of words to explain, and then you need to make a lot of assumptions. So the tutorial questions, right, and some, if you do the textbook question, you know what I'm talking about. Okay, so yeah, I'm not using it. Yeah, so yeah, so don't worry. It'll be mostly like what we have been discussing here, right? So that is basically most of the question is similar to what we are doing. Okay. Although mastering physics has a lot of questions, so I don't know what questions they have, which I stopped using for a long time already. In any case, yeah. So the kinetic friction is like this, right? It's always opposite to the direction of motion. So now we want to talk about rolling with slipping. Okay, so rolling with slipping happens when the V tangential is not the same as your V center of mass. So, and then you guys have already mentioned many cases, right? Like if V tangential is larger and V tangential is smaller. So we are going to explore that now. So let's look at case 1. Okay, so case 1 is, let's say V center of mass is greater than V tangential. So what's actually happening if V center of mass is greater? So we can visualize what is happening here, and remembering this, we can even determine the direction of static friction. So let us see. Very ugly circle, but we can get a point, right? So yeah, so we have the V tangential, and then we have the VCM, but my VCM is greater than V tangential. So let's see what happens at the bottom. The bottom is where the important thing happens, right? So when it's at the bottom, right, when these two are not equal, the two vectors do not cancel each other anymore. What happens if VCM is larger? So let me draw a longer vector, and then V tangential is smaller. Okay, so V tangential, remember, is r omega. If this is longer than this, then the total velocity is here. So the VP is forward. Okay, so the instantaneous velocity when it's touching the ground is moving forward. Okay, So that means it is sliding over the surface. It's hard to imagine so many things happening at once, but equation wise, just see it's moving forward. So when it's moving forward, right, what happens to the kinetic friction? Because there is relative motion between the cylinder or ball and the surface. There is relative motion. The velocity is forward, and since kinetic friction is always opposite, we can determine the direction of kinetic friction. So my kinetic friction is Fk is pointing this way. Okay, so the kinetic friction is in this direction. Then it will contribute a force that is negative, right? If I say right is positive. Okay, so let's see what happens here. We can actually animate this situation. Where was it? Okay, so let me show you the animation. Let me bring this up. Okay. So many things open. Okay, so we want the situation where VCM is larger, right? So yeah, so VCM is larger than this. So at the bottom, this vector is larger than this vector, so the kinetic friction is pointing this way, right? So there's a net force that is pointing to the left, right? So and then if you scrape the wheels, you get this type of situation. But if we go to the other case, right? If V tangential is larger, that means it's overspinning, right? It's overspinning against the ground. So if it's overspinning against the ground, what happens at the bottom? The net velocity at point P is going left, so there's going to be kinetic friction acting to the right, right? So it's overspinning, so that's why you have everything will shoot out in this way, but the kinetic friction is opposite, so it's acting to the right. Okay, so that was the case 2 that I'm about to draw next. Okay, so that is the case 2. So in case 2 is the opposite, right? So my VCM is smaller than V tangential, so is overspinning, right? So it happens this way. Then this is like this, and then you got this, right? And then so what happens here is VCM is too small, so VCM is too small, and then the V tangential is fast, so overspinning. Right, so too fast, that means the net velocity, right, is to the back. So VP is backwards, and because the very ugly, so VP vector is backwards. Because the velocity vector is backwards, how to determine the kinetic friction? So the kinetic friction is forwards. Okay, so the direction of kinetic friction depends on the whether it's overspinning or underspinning. Okay, if overspinning, VCM will change direction. Okay, okay, so first Kai-Xuan, when does wait, no, got this question right? Overspinning VCM will change direction, correct? Yes. So because, right, well, it won't. Underspinning, it will. So as you can see, right, if it's overspinning, we can just use Newton's law. Newton's law, it says that there's a force acting forward, so this object will accelerate forward. So the linear center of mass motion velocity will increase to the right. Okay, but if it's underspinning, right? If it's underspinning, what happens? The kinetic friction is acting this way. When the kinetic friction acting this way, it is a deceleration, right? So it will reduce the speed, the forward motion here. So eventually it will reduce to 0, and we will solve in one of the tutorial questions, it will actually change the direction. So the VCM will shrink to 0, but acceleration is, if the acceleration is constant, it will continue to become this direction. So it will change direction for underspinning, but not for overspinning. Okay, so this is the underspinning situation. What was the other question? when does overspinning happen in real life? Yeah, correct, like when driving. So so imagine you're in a car, right? The car initially is not moving, and then you suddenly press your pedal. I think Zirui was talking about in the previous class, the same thing, right? So if it's not moving, you suddenly press the pedal, okay, like in this animation. So let's say nothing is moving, but if you suddenly press the pedal, right, then if you start to move, it will overspin against the car, right? So that is what happens. Then the underspinning can happen if you are moving already, right? If you are normal driving, then you should be pure rolling most of the time. But if you suddenly hit the brakes, right? If you suddenly hit the brakes, your brake will slow down your V tangential, but the VCM is determined by the momentum of your car. Then it will make it underspinning, right? So it will decelerate the car. So this is the situation that happens here. So if you suddenly hit the brakes on your car, right? So if you suddenly hit the brakes on your car, the brake can actually, usually your brake system will reduce the V tangential, but the VCM is determined by the forward momentum of your car. So it will reduce this, then it will create a friction, right? If you brake too much, then it will create this friction, and that friction, that's why you have the drifting situation where your wheels are sliding over the ground. Okay, so yeah, burn tires. Use finger to press ball. That is where another situation here, correct? Where you basically this one will also cause the kinetic friction. Yeah. So F1, I think F1, when they start the car, usually they burn the tire, right? Or the drag race or NASCAR, maybe not NASCAR, but drag race at least. Yeah, burn tire. So yeah, in F1 usually they need to change tire before they finish the race, right? And they need to change it quite frequently because of all the friction. You're killing, yeah, F1 driver is the tire killer. Drifting is a classical slipping, correct? Yeah. Although drifting, right? Drifting is a situation that is more complicated than what we consider here, because for the questions that we solve, we only consider motion in one dimension, right? But for drifting, you have the X and Y direction also. So that was even more complicated to solve. Yeah, and also like the drift racers, also they need to change tire quite frequently as well. F9. Yeah. Oh, he came back. Okay. When you press something with so much force, the ball will move a little bit forward or backward. Yeah, this one is also a situation that it might be a bit complicated to consider. Han is back, but I thought he's dead, right? So it's underspinning. So the pressing ball is also a complicated situation, because the pressing ball is, let's say you have a ball on the ground. It depends on where you press, right? That's what makes it more complicated. So if you put a force here, then that's the direction, right? And then you need to consider, I don't even know how to solve this, but yeah. But I think if you push it initially, it will be rolling with slipping. Yes. So maybe it will cause a rotation and a linear motion at the same time. That's why it's very hard to solve. But generally speaking, it is slipping. Yeah. So yeah, don't worry. I don't even know how to solve this. But the idea is there. Okay. Okay, so now I can't wait to watch F9. Han is back. So these are the two situations that can happen, right? And actually that's about it, right? So that's all about it for, if you can understand this picture, then all the question is solved based on this idea already. Then we can see how to solve. Okay, so if you press the ball, VCM is positive, but the rolling motion makes it back and VCM negative. Correct. Okay, so but it depends on situation, right? Pressing the ball, if the ball is moving, can you press it? Right? You need to chase after the ball, and then things, right? So, but I know what you mean, is you can do it with the coin also, right? So if you have a coin, right, and then you press at the back of the coin will go forward and then it will spin back a bit, right? So that is the situation we are talking about. So maybe we can try to solve this example, but let us solve one from the textbook first. Okay, so this one is a slightly simpler situation. So let's start with something simple. This is example 6.5.3. Am I recording? Yes. Yes. Marbles. Yeah. Marble maybe more slippery. You're right. I can imagine this happening for coins, or I think if you play bowling, right, it also depends on how you throw the ball. If you throw the ball that is rolling in the wrong direction, it will eventually roll back to the correct direction. Rubber balls, yeah. The friction contributed by V tangential provide the opposite direction. We contribute to ACM. Correct. Yes. Yeah. So this is the type. This is what we want to do here. Let's look at the example. So I think it will be clear after we solve at least one example. Okay. So is this. So this is kind of something like the coin. We have a uniform solid disk of mass m, radius r. So it is a solid disk. So it's half mr square, right? The moment of inertia is half mr square. Okay, so it's set into rotation. So the thing is spinning first, and then while it's rotating, right, when it's spinning, you place it on a rough horizontal surface and then you let go. So the coefficient of friction is this, and then we want to determine when does pure rolling motion takes place. Oh, this one is yeah, bend it like Beckham. This one is we won't learn this in this course. It will it's something to do with turbulence and things like that. But it's very interesting. Yeah, we can kind of explore this later if you have time. So let's try to solve this. How do we figure this out? Okay, so in this question, right, we have a spinning disk. Initially, it's not moving. So initially, V is equal to 0. So I'm lazy to write Cm everywhere. So this is the Cm, right? Initially, V is 0. But the omega is some initial angular velocity that is non-zero, right? So that means initially, it is spinning against the ground. Okay, so initially V is spinning against the ground. So you can imagine, right? At the bottom, so at the bottom, my V tangential is here. Okay, and then the VCM is 0. So there's a V over here, right? So initially you put a spinning object and then you place it on the ground, right? So you place it on the ground, it's spinning against the ground. And as it spins against the ground, the V is here, and we can imagine because the kinetic friction direction is opposite, so there is a Fk in this direction. Okay, so there's a Fk in this direction, and we can get the other forces as well. There's a mg and there's a normal force. So later we can use this to determine the magnitude. So Fk times the normal force. So normal force is equals to mg. Okay, so initially you put this over here, and then let us see what happens to the motion. Let us draw the translational motion by the free body diagram. So translational motion. So to get the translational motion, we look at the free body diagram, right? So it's just only one force acting in the forward. So we take right to be positive, right? So the only force acting on this is only Fk, right? So and then yeah. So by the way, there's a vertical for vertical forces. The n balance out with the mg, and then the horizontal forces is where we take right to be positive. Is the net force is equals to mass times the acceleration. of the system. And this Fk is given by mu kn is equals to ma, and the n is, from here we know already, is equals to mg. So we got mu k mg is equals to ma. So from here we found the linear acceleration of the system is mu kg. Okay, so this one is just the linear motion. We solve it in our normal way from chapter 2. So nothing special about this, right? Get the free body diagram, get the acceleration. Oh, okay. So you guys are talking about this, right? I want to talk about this later. So let's talk about this after. Yes, this is an interesting case. So I want to discuss this after I finish this problem. Okay. So I have the first expression over here. Now this is a constant actually, right? So this is a constant. So A is constant. So we can use this formula. So the speed is just the initial speed plus at, okay, where my a is this one, and this is 0, initially at rest, right, initially 0. So I have v is equals to mu kinetic friction g times t. So from here we have solved the linear motion already, right? For a spinning object, because there's a kinetic friction, there is an acceleration, and it causes the velocity to increase with time. Okay, so velocity increases with time, the linear velocity. Now let's look at the rotational motion. So for rotational motion, we look at the torque. So what is the torque acting on the system? It is spinning, right? So the net torque, well, there's a force of mg, and then there's a normal force, and then there's a friction. We have drawn the friction to be this way, so Fk, right? So the net torque is equals to, well, there's the distance is r, perpendicular is 90 degrees, so r times Fk, and then there's 0 distance of n from the axis, so 0 times n, 0 times mg. Okay, so these two numbers are 0. And then Fk also we have determined, right? So Fk is equals to mu k mg. So the net torque acting on the system is R times mu k times mg. Okay, and then next thing we use the rotational Newton's law. So the torque is equals to I times alpha, right? We have determined the torque already, so it's R mu k mg. This is a disk, right? So it's half mr square, and then alpha. Because this is not pure rolling, alpha is not equals to a over r. Okay, so this is important. Yes, Magnus effect. Yeah. So the path will be strange. Yeah. So yeah, so Magnus. That is what happens with the ball spinning in the air, right? Okay. Important thing to remember, this is rolling with slipping. So I have slipping. That means alpha is not equals to a over r. Okay, so it's not equal, so I cannot do this here. Okay, so yeah, I cannot do this here. So let's keep it as alpha. But what we can do is we can cancel the r and cancel the m, and then what we have here is alpha is equals to 2 mu kg over r. Okay, this is also a constant, right? All these are just constant numbers, right? R is a number, mu k is some number, everybody here is constant. So if it's a constant, then we can say that omega is omega 0 plus alpha t. So we can put this into here, so that we find that omega is equals to initial omega, which is non-zero, right? Initially you put it spinning, and then alpha is oh, by the way, yeah, this is where you have to be careful. Direction is important. The torque will cause a deceleration, right? If you put it on the ground, it will slow down the rotation. Okay, so to capture this information, right? So let us say that we say clockwise positive. Okay, so clockwise positive, and then this will cause this torque will be hang on, let me say anti-clockwise positive. Okay, so if this is anti-clockwise torque, then it will give a negative contribution here. So this is the mistake, I forgot. So let's correct this. So the torque will give you this, so it will give you this, then it will give me a negative acceleration. Okay, so this is a constant deceleration. Still talking about Magnus effect. Actually, I have seen a video that you do the Magnus effect with something like a basketball, but you need to drop it from a very, very high height. So like a very tall building or a very tall dam. Then you can see the, yeah, this one, basketball. Introduce cross product will make it much easier to determine. Yeah, you're right, but yeah, although the idea was, because cross product is still new to many students, right? So we try to we didn't use cross product here. Okay, so we substitute this into here. I got a deceleration, right? I got 2 mu k g over r times t. Okay, yeah, so I have these two equation over here. So actually this is not the important one. This is the important equation 1 and equation 2. So we have solved the system already, right? We using the torque and the free body diagram, we have calculated how the linear velocity change over time and how the angular velocity change over time. So you notice that the linear velocity is increasing, the angular velocity is decreasing, right? So this is what happens here. Okay, what time is it now? So we want to find the time when pure rolling motion takes place. Okay, so that is what the question is asking for. So when does pure rolling motion takes place? Because initially right now what we have is not pure, right? Because it's not the same. So when does pure rolling motion takes place? It happens when the V tangential is equals to VCM, right? So in other words, R omega is equals to the VCM, okay? And I have my omega here and I have my VCM here. So I have R omega 0 minus 2 mu kg over R times T, and then V is given by this, so it's mu k gt. Okay, so now we can simplify this equation. So we got R omega minus 2 mu k gt is equals to mu k gt. So I got 3 is equals to R omega. So I can find the time when this happens. Did I make any mistake? Omega 0. So R omega 0 over 3 mu kg. Okay, so this is the time where it takes place. Okay, then for part B, right, the question that we want to solve for part B is what is the angular speed when once pure rolling motion takes place. So for part B, when pure rolling motion takes place, this is where the time it happens. So what happens to my omega during this time? So my omega during this time is, we use the formula, so it's minus 2 mu kg over r t, and I want to find out my velocity for this time. So I put it into here. So omega is omega 0 minus 2 mu kg over r. The time is r omega over 3 mu kg. So I can cancel this and I can cancel the r. So I got omega 0 minus 2 over 3 2 over 3 omega. So my final omega is just 1/3. Okay. Yeah. So yeah, you guys are talking more advanced things. So um, the ball is spinning as the bullet. Can you move faster? Pass the ball. Well, anyway, let me finish this question first, right? So what happens here is that I think it will help for us to draw our situation. Okay, so what happens is this: we have solved the v against time. We have also solved omega against time. Okay, and based on our solution, my v is just a linear function of t, right, with the slope mu kg. So initially my v is 0, and then it's just increasing linearly. Okay, so increasing linearly with time, and then my omega, right, is this decreasing with time. So omega is initially at omega 0, and then it's decreasing in time. Okay, so until when pure rolling motion takes place, so pure rolling is maybe at some time here, this value. Okay, then this is the point where r omega 0 over 3 mu kg, right? Once this happens, right? So once this happens, once this happens, v is equals to r omega final, and this is omega final, right? So this is when pure rolling motion takes place, right? So when and then omega final is just 1/3 of my initial omega. So during this time, this is rolling with slipping. And then from here onwards, it will become without slipping, so pure rolling. Okay, so this is rolling with slipping. And then after this time is pure rolling. Okay. So initially you put something spinning on the ground, right? Basically the system that we are solving is that you put something spinning on the ground, it's overspinning. If it's overspinning, it will start to go forward, but the VCM is not equal to the V tangential. But the VCM is increasing. So it will increase, and then at the same time the V tangential is decreasing. So it will, one is going up, one is coming down. It will increase until they both meet at V is equal to R omega. So they will reach a situation where the V tangential will become the same as the V initial. And once this happens, then after that it will become pure rolling already. Okay? Does that make sense? Do you understand? So yeah, so the Magnus effect is this. The Magnus effect is a combination of turbulence on the ball and the non-equal forces lah. So why the bullet is spinning? I don't know. Is it something to do with this anime, which I don't know? But generally, if you just talk about a gun, right? The gun is actually by design they make it spin. They purposely want to make it spin, and it's called the rifling. So yeah, so gun barrel rifling. So you see inside a gun, right, there's this spiral shape, and it will cause the bullet to spin. When the bullet spins, right, it can make it travel more straight. It's more stable, correct? Yeah. So it will, and the reason is also partly conservation of angular momentum. So if it's partially aerodynamics and partially conservation of angular momentum. So when the bullet is spinning, right? So when the bullet is spinning, there's a rotation here, and then the axis of rotation is parallel to the direction of motion. Okay, so so when there's a angular momentum with this axis in this direction, you need extra force to make it change direction. So that means it will cause the bullet to remain going straight. So that if there's a wind and turbulence and air friction, it's not enough force to cause it to change direction. You need a high force to change a direction of a rotating axis. This is something that we haven't learned yet because we're ignoring all this. Call of Duty. Yeah, so there's also like a lot of interesting thing when you design games. Some games they simulate the bullet drop over time because bullet is a projectile and the drift and things like that. So that is also like a lot of physics to explore when it comes to that. Okay. Wow, it's already 11:54. So does anyone have any question? Right, so everybody discussed until the Magnus effect, but is everyone okay with this part, this problem? Right, if you are okay with this problem, then I think maybe on Monday, whether I start a new chapter or I think of another example. So maybe when we do tutorial, we will explore this problem a little more. You missed the whole question. Don't worry, because now we have video, right? So you can watch the video later. Oh, PUBG. Yeah, Battlefield, they simulate the bullet drop. For Call of Duty, right, you just aim and then they assume travel in a straight line, so you just click on the target, you hit already. But yeah, so especially if you play games like Dark Souls, if you shoot bow and arrow, right, the arrow will drop like a projectile. Or CS:GO. CS:GO also no bullet drop, right? The original Counter-Strike, no bullet drop. Yeah, like laser. My recording time is negative sign. I don't know why. Yeah. Approximate to nothing, huh? Yeah, I don't know why my recording time is negative. It's weird, right? But I record the OBS also lah. So OBS is working properly. So at least got backup. Direction wrong. Yeah. The time direction is wrong. Maybe we are going backwards in time. Yeah, so don't know why. But in any case, I guess that's the end of the lecture already, right? We finished chapter 6. So after this, we have exam. After exam, we start talking about gravity now. So yeah. Okay, so if there's no question, then that should be all for today. I shall stop the recording.